And we can start reading from training models across multiple devices. That would be page 701 in the book. And we can try to get to the end of the chapter. Let's see how it goes. Let's reconvene at what do you think? 8:20. That would be what, 7:20 Pacific time.
Yeah. So, what sections are we reading again?
On training models across multiple devices on page 701. I don't know if he's too ambitious to try to get to the end of the chapter.
Oh, let's try it.
Yeah, let's try that. And we can reconvene in about 50 minutes.
Yeah, 7:20 or so.
Yes, 7:20 Pacific time.
Yeah. Okay.
Okay.
Yeah.
Oh, hello.
Hey.
Yeah, somebody had somebody could get to the end of the chapter.
Yeah, just that was yeah, going till 7:30 helped.
Okay, that's good. Okay, let's start with this. So now we get to train our models across multiple devices, multiple GPUs, multiple servers. So for this we need to do parallelism, and there are two main ways, like model parallelism and data parallelism. So for model parallelism, the model is the first approach can be trying to get the different layers and different GPU devices, for example. But that would make the second layer to wait for the first layer to be complete, and also because the wait and the transfer is going to be very slow, that's what you're saying. And there are this is the model, right? And then it can also be split vertically, right? Different cells of the models on different devices. It's a bit better, but not so good. Yeah, for example, these on the left side here, the first layer is trained, and then the second layer starts. But you need to wait for the first layer of the other device to be complete to send the input. So there is cross inputs, right? So it's still not good, right? And then there are like CNNs that has layers that are like only partially connected to other layers, to lower layers. Yeah, for example, on this left side, right? Those cells on the left side are connected. For example, this third layer only dependent on the left side on the second layer. And on the right side, they're also independent, right? So this is a good candidate to vertical split. And that's why it's showing on the right side in the diagram. Okay, and we have, for example, from the first to the second layer, there is cross talk or cross communication needed. Yeah, because yeah, on the left side, for example, on this architecture on the left, the right side is taking the output from all the first layer. It's only showing this part, right? But this represents all the first layer as input of this second layer on the right side. So that's the same thing. So on this partitioned representation, the second layer on the right side still needs the input from this, the first layer on both parts, right? So there is still need to get the outputs from the first layer across, right? But after that, the third layer only needs the second layer on that side of the partition. So there is, on this way, there is no cross information crossing across the network. So this has better performance. And they say that this is fairly good. They say so. Okay. What else? This is Yeah, there is also the deep recurrent neural networks can be partitioned a bit differently. They can partition like in stages, right? So the first cell starts on the first device, and then okay, let's see. Yeah, I got a bit confused here with the progress.
It's just a recurrent neural network with the time steps. So yeah, here on a single time step from the left to the right, 1, 2, 3, 4, 5. So and the base layer we have uh, those time steps, and you can see the receptive fields that are decreasing at every step here. So and this is being replicated here. So on one GPU, we have these cells, the internal representation of a RNN, the hidden states. This is the first hidden state, you can say. This is the second, third, fourth, this cells, and they are being distributed all across a single GPU. So this is a specific case of recurrent neural networks.
Okay, so uh, okay, so it means like for these cells, the different steps, right?
Yeah, this
One,
is
two,
a
three, four, five.
different time steps. Yeah.
Okay, and
Here,
then
here we can have a, you can see it as a recurrent, deep recurrent neural network. You can see it as a Tesla's a self-driving car. You can even Karpathy had a talk with regards to this on how multi-heads in a RNN can be used as a uh, how do I say it? The inputs from the cameras can be fed into RNN, and those six cameras and radar sensor can combine those inputs uh, firstly and then feed together in an RNN cell. And these cells can be distributed across the GPUs or a particular subsection of a GPU, whatever way that they have implemented it in their self-driving cars. So uh, that was one of the insights that I got when I watched this talk. That's the example that I relate to it when I understand these.
okay. So this first cell keep running on the first device, right? Okay, and then after the first step, the output gets to the next cell as first step, right?
Yes.
And also its own second step, right?
So yeah, these weights and those hidden values are propagated. And in case of combination of images, there will be a huge matrix here. So that would have effect of, how do I say it, that large image. So those matrices must be decomposed. So the first input that we have here, this might have the first image, and you can see in the next time step, this might be propagated to the next GPU here, and this way, and yeah, those inputs might be fed here, yeah, and those outputs we get according to this. So yeah, this is one formulation. The architecture, of course, differs. with respect to the different, how do I say it, the tasks that we want to perform. But this can seem like a image to caption task too, where an image is where a sequence of images are fed in a video, and yeah, each of the frames are and you can say this is the first frame, this is the second frame, this is the third frame, fourth frame, and the fifth frame, and we can have those outputs relating to what the images, what the objects are in an image. So image to uh, uh, text caption. That this can be a very good example of that. Or if it's uh, that uh, in the last layers, those texts can also be replicated. That can be replaced, sorry, with the particular action. So if there's a self-driving car here, so yeah, their action can be go left, right, straight, or have those accelerate or decelerate depending upon the uh, images that we saw earlier. And that's the receptive field that is being decreased across uh, yeah, every hidden internal layer.
Okay. So this is okay. This is going to be escalating, and then at the end, the last cell is going to be run by the last step on the last device, right?
Yep, we can have some sort of a
something like this, for example, like this, right?
Yep.
Okay. Okay.
Yeah, but it also depends upon the number of inputs that we want. Yeah, that this can be continuing in a continuous time space too. Yeah.
Oh, a continuous flow. Okay, I see that.
Yeah, continuous flow too, or depending upon the receptive fields, it can have that particular uh, the sequence of images in a video uh, uh, initially, and based on that, we can use them to determine the confidence levels of, suppose, the initial 4 or 5 frames have the most effect. So, depending upon the outputs here, which map, because in the last stage, those 3 or 4 inputs are kind of missing if we are starting from the initial state, or we can have those, how do I say it, uh, kind of adding that can be applied here to like in wavenets, if you have come across that. In the DeepMind's wavenet, uh, they had a similar kind of a convolution based architecture uh, in which the receptive fields yes, yeah. And if we can quickly open this wavenet generative module raw audio, there's a very cool animation which
Okay, what is that? In the
which
chat?
shows the, yeah, in the chat. Uh, scroll
I'm
to
still drawing or something like that.
yeah, just scroll to the
Okay.
the second section of the image.
This one.
No, just below that. Below that. Yep, there's this one. I think, yeah, this will give a much better intuitive presentation of the.
Okay. That's nice. Okay.
Mm.
Okay, let's continue with this. Thank you, Majang.
Yeah.
How do I remove the annotations here?
Just go to the drop down from that, and there's a clear button. Annotate, and then there is a clear from the top right. There's a trash can here icon. Yeah.
Okay. Thank you. Okay. So that's for model parallelism. Then the other way is to do the to distribute, use the data parallelism. This is more usually used. Okay. So in this example, is the mirrored strategy, where the model is the same in every device, and you use partition the data in mini batches and different batches for across the devices. And they work in parallel with different data, and then at some point they get a mean of the output, and then update the parameters, and then get again the cycle, right, for other mini batches and so on and so on. Okay. They say here that it's quite efficient in a single machine. Okay. And the problem can be when trying to get the gradients across updated. Okay. And there is an algorithm they call here reduce. It's a class of algorithms to do this efficiently. Okay. And there are off-the-shelf implementations, so we don't need to implement those algorithms by ourselves. Well, that's one way, right? With mirrored strategy. And then there's the other, like the car. They use a parameter server. That's a separate server. Then we have also mini batches, but they work differently, separately. And at the end, the outputs get to the parameter server, where it gets the mean and the updates on the parameters that are again provided back to the these models. And then again, the mini batches are put as input, right, on those, in this case, three instances, right, three different devices. Okay. And there are, on this approach, there's two ways. There is synchronous and asynchronous updates. Okay. For the synchronous updates, let me see if it's there. Here, there's not. For synchronous, once the each device finishes the execution, it goes to the parameter server, and until all the devices are complete and provided the results, the outputs to the parameter server, then the parameters will continue to do the mean, to update and update the parameters and back to run again, right? But to make that a bit better, because you have to wait to every device to finish their part of processing. They use like spares, right? So in this comment here, they have 20, let's say 20 devices running. And then in this case, there is like 18 replicas, they call that, and plus 2 spare replicas. So once the parameter server gets the output of 18 of the 20, it continues and say we're good. We don't need the other 2, and it doesn't wait. Get the mean and provide the update on the parameters with those 18 replicas. Right. So let's say this works if you have like a couple of slower GPUs or that for the data were slow, so it should improve performance, right? And
just to ask a quick query, how does this affect here with respect to the replicas that we have? Because that may crash too. Still, the training will continue as it is alluded to in the index. Sorry, in the appendix of this chapter. Because this is just equivalent and they work hard to be the fastest at each training step. And as the loss varies at each step, it's a bit confused about what the implication of this is.
What the implication is, I would think that
it's just that the 18 out of the 20 will finish faster than if you wait for all 20, and then so it's saying that just wait for the first 18 to finish, and then throw away the results from the other. Don't even wait around for the results from the other 2. Just use those 18 replicas to compute the parameter updates, and then start a new round. And what he says is that if one of the servers crashes, then you're still okay. Because you only need 18 out of the 20.
So
even if 2 servers crashes, you're okay.
Yeah. Okay. So that's the redundancy that we have with respect to the risk assessment, the risk that can be thought of. Okay. So doesn't this? Yep. I got the just that it's being replicated, but doesn't this have an impact if? I guess it doesn't, because the losses are the same. Yeah. Okay. Yeah, I got it. Thanks.
Yeah, you might say that some mini batches are not going to be accounted, but there will be only a few, right?
Yep.
Those are going through this. For example, if we have in 3, like this case, right? 3 devices and this one and 1 spare as configuration, let's say, if the third one is not going to be accounted, right? It's but
yeah, and so your parameter updates will be slightly less accurate. If you use 18, of the replicas instead of 20, then your updates aren't going to be quite as accurate as if you use all 20 of them. But I guess it makes it up because it's faster and it's fault tolerant as well.
Yeah, more robust. Yeah, that's a good point.
Quick question with figure 1919. So the parameters are still there on ABC, right? It's just that the parameter update is not happening on ABC. The first 3 machines still hold it. The parameters just sit on the server where the update happens, right? That's the difference between this and the previous one.
Yeah, I guess this is where you use the CPU for holding the parameters instead of
the GPUs. Yeah.
Okay. And at this point of 18 and 20, like why, I mean, I'm just trying to understand why would like some be slower than the other? Like, is it just because you have, I mean, I'm trying to understand, like if you're using like a lower end GPU, why use that GPU itself? So I was just trying to understand what are the other reasons, like why you would want.
Well, maybe one batch is harder to predict. Maybe one batch is, somehow different than another batch and needs more calculations. Or maybe the GPU is just naturally slower. Maybe the GPUs have a slight variation in speeds.
Yeah, it might be also failing, right? There will be some fault on that GPU, maybe.
Okay. Cool, thanks.
Then we have also the asynchronous updates. Okay. It doesn't wait. It just uses as they are coming. Right. Yeah, as there is no weights, it can be it can have better performance, but there are some caveats, right? Some inconvenience, right? For example, here you get one computation, right? One computation here at this point, right? And then when the computation is complete, you get this gradient, right, on this direction. But when you get it and you want to apply it to the parameters, actually, they have been updated by the other replicas, right? Like a different jumps on the output of the other replicas. And at the point of application, the status is a bit different. And it can throw the model, the training of the model away from the optimum, right? Like this example. So this computation is stale because it's no longer accurate, right? So one way to avoid that is to decrease the linear rate, so to make the jumps smaller, right? So I would guess that this is automatic, right? In some way.
So I don't understand the next one. The next one says drop stale gradients or scale them down. But how do you know which gradients are stale? I mean, in other words, if they're all stale, or how do you figure out which ones are stale?
Yeah, I would say, well, I think it's automatic, right? But that's a good question. How does the algorithm determines how either is stale, right? I would say if I was the programmer, I would compare this update against the latest ones or the more newer ones, and if it's too large compared to the others, I would say it was jumping farther because it was farther away from the optimum, right? So if you're getting smaller updates from the latest replicas, it means that these replicas think you're close, right? And if this one has a big jump, you can say, oh, this was calculated when the status was too far away from the optimum, right? Something like that.
Yeah, I'm wondering if you actually, to do that, you actually have to store all of the previous updates. Although I thought with asynchronous, you just apply the updates and then forget them. But for the method you're proposing, you'd have to remember all of the previous updates so that you can compare the current one and see if it deviates too much from them.
Yeah, one other way that this could be estimated is if the if the timestamp, for example, of this update was like too old in average from the others, you will say, oh, this took too long. It might be too old. It might be bad. It might right something.
Yeah,
like that,
that's a good point. I mean, you always have the clock. You know, you always can refer to the clock. And then the last one, adjust the mini batch size. I don't quite understand what they mean by that, because if you make the mini batch size smaller, then the updates get noisier. So
yeah, this one goes over my head. I don't know.
Yeah. But I think it's all moot, because a couple of paragraphs, one paragraph later, he says that a paper published by Google Brain compared these two methods, the synchronous and asynchronous, and then decided that the synchronous ones usually converge faster and produce a better model. So
yeah, they are saying that, right? But I have heard that this asynchronous is the most usual, right?
Is that right? I don't know.
Yeah, that's what he was saying here, right? Okay. Anyway, but this is more complicated for sure.
Yeah.
Since I think so, there are in the asynchronous case there are multiple workers in parallel, and then they communicate with the parameter servers, and they are processing their mini batches independently. So if when we are combining, which is obviously very much different to those of the serial computations of the stochastic optimizations, this may have an effect of the parameter interleaving with respect to the weights that we get from the different parameter servers. So that might not be consistent with the like those asynchronous updates are not consistent with when we combine them back together. And the second reason is, as it has been indicated, that since while one worker might be computing its stochastic gradient, the gradient are typically computed with respect to those outdated parameters. So one might have finished, and the other might still be computing. So the slowness, the staleness here, as you alluded to, that might also have an effect on the updates of the read and the update operations that we do for combining them. So that's I think so, the reason why the staleness becomes a factor.
I don't understand the whole strategy this way, because it seems like when you do these asynchronous updates, you're sending the unit, you're sending the workers on a wild goose chase, because every time, they compute an update, that update might be stale and may not even be used. And the actual parameter update gets done sort of randomly, depending on who finishes first. And you're not using all the data. Like in the synchronous update, you use all of the results of all the workers to calculate the update. So there's a benefit there. You're getting less noisy updates, because you get to average over say if you have 16 workers, you can average over 16 results, and that cuts down your error by a factor of 4. But if each of the 16 workers gets to update whenever it feels like it, whenever it finishes, it gets to update the parameters. And then the other ones that are already processing, their results might become stale and useless. So I don't understand this whole strategy, actually.
That's the point of this. You defined the problem perfectly. So yeah, and that's why synchronous is much better. But yeah, that will have an impact on the time. But if we can model it with respect to those asynchronous operations, then specifically in this case, they may converge faster. But yeah.
Well, even though the whole idea is that asynchronous is supposed to be faster, but then this Google paper found that the synchronous updates converged faster. Anyway, so the point, so it's all, the whole point of using, one of the whole points of using the asynchronous updates is to gain speed, so you don't have, because you don't have to wait around for all the processors to catch up with each other. But then that gets that ends up not being an advantage in the end.
So you can say that because of no waiting, you end up dancing around, right? Something like that.
Yeah, I mean, you save some time instead of waiting. You get the updates faster, but each update is weaker. It's noisier. It might be stale, So yeah, that's why I don't understand the strategy.
Well, Joseph, I'm trying to understand this discussion and trying to get a little better sense of it. All of you are talking specifically about how at the end of the day, the model will converge. But is it really about the model, but more about the data? And so wouldn't this tactic be specific based on the data being used? What is the data? How, just say you're working with COVID-19 data, whatever. Isn't it more about that? And this is a strategy, this is a tactic that one can use to try to get a model to converge. But just as we build the neural networks with tuning the parameters in certain ways or so on, this is yet another approach to see if it works with the data set that you're working with.
Well,
maybe
this is an approach that is designed to work with multi-processing environments, when you have the option of having parallel processors at your disposal. And so it's a way of getting, these are two different strategies of getting parallel processors to work together to train a model. So it's about the training process rather than the data. I think you can think of this as working on any kind of data. It could be image data, it could be text data, whatever.
I was thinking more of the real-time incoming streaming data.
Yeah.
Stuff of your IoT or stuff of real-time, like you've got different populations of people that you're measuring certain things. But you're, okay, I see.
I've shared the paper that they referred to in the text here, and they have a couple of graphs which can help with the convergence and the time that are required for the number of workers. Just looking at it with the sync and the asynchronous operations, the difference between the synchronous and the asynchronous operation, the time, the precision, the epochs, the mean time that is required. So I've shared it in the chat. You can open it up. Yeah, and on page number 7, they have given a difference between. Yep. Here there are green and blue lines. The green represents the asynchronous and the blue represents the synchronous. Yep. With respect to the epochs, the time, the mean epoch.
Yeah, so it looks like for this task, just one processor, that's the blue, beats both 8 asynchronous processors or 16 asynchronous processors, the red or the green, in terms of minimizing the function, the time that required to minimize the function to a certain level.
Yeah, for this was a pixel CNN, and if you scroll up to the figure 8, yeah, this is with respect to the inception model on which they have tried.
Yeah, so synchronous converges faster. It needs fewer epochs.
The higher test accuracy. So yeah, that's the whole reason it out and the things that we were discussing.
I think the bottom line is not yet developed enough to use it, so don't use it yet.
Yeah. Yeah.
I think there are other ways to get around this problem rather than going into the async mode.
Yeah, I mean, to me, something that's easier to understand and works better is a no-brainer. I mean, so the synchronous.
Yeah, we can say that the asynchronous is like too smart, right?
It's good to know it exists.
Yeah, smart. I would only think in one scheme where it may make sense if we have like a noisy network or something like that, where you don't get like at least 18 of 20 replicas to be completed or something like that.
Yeah, the thing which I can still not wrap my head around is like what Joseph was pointing to, like how can you use gradients which are not updated to update the next gradient? So that, I think he also makes a point. It's surprising that it works.
Yeah.
Yeah, so, I saw that.
So again, with neural networks, it's one of those things, right? It seems to work. Don't know why. But this one doesn't even work as good as the sync. So yeah.
Okay. Yeah, good point. Good to know that this.
I mean, I suppose you could use some kind of an exponentially weighted strategy so that if the new update gets too far out of line, it gets de-weighted, you know, and
it goes back to your problem of kind of saving that stuff, right?
Yeah.
Oh, actually, no. Actually, if you're doing an exponentially weighted average, probably you can get away with it, like momentum or something.
Yeah, just comparing the new.
Right.
Well, you still have to remember the last update, right?
No, you just probably weigh the last one higher, right? You'll weigh the last one like 0.9 times, and the new one coming in just 0.1 times. So you don't have to really store it. You can kind of, I mean, exact momentum strategy if you use, I think we can get away with storing stuff.
But the last one will might be the stale one, and that might.
Yeah, that's why you're still taking.
But you de-weight it. Yeah, so that's why de-weighting it would minimize would mitigate the impact of such a stale update.
Yeah, but you need to know that it's stale first, right?
No, I mean, without knowing it's stale, every new update is basically taken only at a lower percentage, right? You're believing the older stuff more than the new.
Yeah.
Yeah, in reinforcement learning, these policies can be iterated. I'm on a tangent here, but yeah, these policies can be iterated and sharpened based on the value iteration or some sort of a Bayesian approach with respect to that value iteration part. So, since I think more from reinforcement learning perspective nowadays. So that's my.
I heard the word policy, and then I thought, he's thinking reinforcement learning.
Yeah. So yeah, that might help with respect to the convergence. Because that this can be modeled as an MDP too. The time dependent MDP that many of the folks have done it in the RL community. So yeah, maybe there is some research that goes to the depth of it, but yeah, since it is an active area, so. Yeah.
Okay, let's continue to next. So the one problem with this is saturation of bandwidth, right? So because information need to be moved around and shared. Okay. And at some point, when you increase GPUs, you might not get an improvement in performance. because you can get all problems like, for example, bandwidth saturation, and maybe training is slower, right? And he's a tip or recommendation that, for example, for small models on very large training set, it's better to use a single machine with a powerful GPU, right? And a good bandwidth in the memory, instead of putting more GPUs or more servers to the training. And here is a part that I don't think it's explaining, right? It's saying like for dense models. Okay, yeah. For example, this example, Jeff Dean from Google Brain. Yeah, he's saying that speed ups for dense models across 50 GPUs is from 25 up to 40 times, right? That means that you can get like, let's say, 50% up to 80% of the GPU put to the problem, right? That's for dense models, and for sparser models, you can get 300 times speed up using 500 GPUs. That will be like about 60% of the capacity of the GPUs, right? But it is not saying that here. It is not saying that when you try more GPUs, you stop getting improvements for dense models. I know what I'm saying makes sense.
Yeah, I think he doesn't say that explicitly, but I think he means that if you go higher than 50 GPUs for a dense problem, you don't get. He didn't say this, but I think this is what he meant implicitly, that you don't get your speed ups isn't as good as when you use 50 GPUs. Whereas he said when you're using sparse models, you can reap the benefits of this all the way up to scaling it up to 500 GPUs. You can still get like 60% usage.
Yeah. Well, yeah, you can read that between lines, but it's not clear that.
Yeah, it could have been stated more clearly, but I think that's what he meant.
I thought those 500 GPUs was more like a typo, and that should be a 50 GPUs for it to be an apples to apples comparison.
Yeah, but it's 300 and 500. And I think he's trying to point to this.
About sparser versus dense, right? And
yes.
he's trying to make the point that denser models, because it has so many more weights and gradients, it's going to be slower. Though in the sparser case, that's going to be less. So it's going to be faster. I mean, the bottom line is that now I'm just saying that the denser model is going to be slower than the sparser model.
Yeah, but he's actually talking about scaling, because he says, as you can see, sparse models really do scale better. And that when he says scale, he means, you can apply more GPUs to the problem. So I think he could have said it better, but I think that's what he means with a sparse problem. You can use lots of GPUs and still get a benefit, whereas with a dense problem, maybe there's a limit.
Well, isn't this hinting to some of the more the OpenAI models? So even at this number, you're running 500 GPUs. That you're looking at a cost of somewhere like $12,000 for the day, typically. Just doing a rough arithmetic in my head. And so this is the stuff of like the OpenAI's latest model. Oh my God, why am I blanking out? Mayank, help me.
Is it GPT-3 or?
GPT-3, which cost 10 to 12 million. in computational time. I mean, that's basically it, isn't, and so this example is for rank brain. So isn't that hinting towards like that particular capability when you distribute the model training?
I'm sorry, what capability? Or
distributed training across multiple GPUs, like a lot of GPUs.
Yeah.
I think the rank brain one used the convolutions and the OpenGPT and used transformers. So that is a bit of a different difference here. But yeah, this talk was given in 2016. So there, what Jeff Dean said then was with respect to the properties that hardware that approximates to deal better with the true zero values and the very low precision activations, the stochastic bit. And yeah, that still holds true, and that has been actually the points that Jeff Dean raised has been implemented in the newer A100 series, the GPUs by NVIDIA. Those sparsity components have been added to it, and the speedups are enormous. So since 2016 to 2020, this progression has holding true. So
okay, well, it gives some examples, right? And these are good improvements: 6 times for 8 GPUs, 32 times for 50 GPUs, 300 for 500 GPUs, right? They're talking about 60% and plus of the advantage of using the usage of the adding a lot of GPUs, right? And for some case, it says dozen. That's start to getting degrading performance. And for dense models and hundreds GPUs for sparse models, right? What, yeah, what the Joseph was saying above, right? And this is active research stuff, because he's saying like they're looking like for peer-to-peer architectures and low C model compression, and when and what the replicas need to communicate, and so on. So this may be changing in the near future. That's what he's saying. Right. Okay. So in the meantime, he recommends using a powerful GPU instead of many weak GPUs. And make the servers very well connected with high speed, maybe. And decreasing the precision from 32 bits to 60 bits. Right, this making the data half the size, decreasing just a bit the convergence and the precision, right? Then if you have a centralized parameters like the parameter server, you can split the parameters across multiple parameter servers to avoid bandwidth saturation. And that's here, right? Now we can keep going here, but there is more like code, right? So what do you think we go here and try some of the code on the left side for a few minutes?
Oh, sure.
Yeah, and anyone, I'm not very clear on the code. Somebody want to or wish to give some input on the code here, or we can just go ahead and run it? Okay.
Yep,
Yeah.
we will help out.
Okay. Let's run this. Okay, this is just clean up, right, and stabilizing the randomness, and then create a model on different layers. Oh, by the way, this notebook is running an virtual machine that Knitting had the graceful gesture to give me access to, because I cannot get more than one GPU. But this server where this is running has 8 GPUs, thanks to Knitting. He was helping me yesterday to get this place running. Okay.
What did you say? 8 GPUs?
Yeah, this has 8 GPUs. It should be here.
Ah, nice. So you got access to...
Yeah, 8K80 GPUs.
Ah, nice, great.
Yeah, so we can test something, right? Okay, so this is, I think this is, okay. I don't remember, let me see. Okay, and create a model. And then this is going to, okay, and train. And while this is training, we can check the GPUs, and we see that only once is being used, right? About 80%.
Is this your machine or?
Yeah, this is the virtual machine in Google Cloud.
Oh, okay.
Yeah, this is not mine. This is from Knitting.
Mm-hmm.
Yeah. He gave me access like a couple of days to make this, help this presentation.
Mm-hmm.
Okay, and then this is running right. And then in the next cell, there is running with different number of GPUs. Let me remove this. Okay. Yeah, like for example, let's say run 2. Next, we're going to run 2 GPUs, right? GPU 0 and 1.
So we are using the mirrored strategy here?
Yeah, mirror strategy. Yeah, we can run with 1. But I already did that earlier today. And for example, when I was running with 1 GPU, each epoch took like 10 seconds. And when I increased to GPUs, the epoch time reduced to 8 seconds. But after that, the epoch time, the training time increased, right? For 3 GPUs, I got 9 seconds. For 4 GPUs, 11 seconds. And for 8 GPUs, I got 19 seconds.
Are these different separate GPUs, or are they sort of divided on one GPU? I mean, parceled over.
They are different GPUs. They are not partitioned GPUs.
I see.
Yeah, not virtual. But,
so
actually,
then that would explain the time increasing as you go to more and more GPUs, because their physical separation starts to matter.
Yes.
Communication in between them.
Yes. And yeah, for example, this is complete, and this okay, let's this took like 10 seconds, right? Each epoch. Okay, that's what I got here. Okay, now let's run this with 2 GPUs. Okay.
So we could also change the settings from, since this currently uses cross-device ops for the mirrored strategy constructor. I think that's the default with the distribution scope that you're trying to build. sparse categorical entropy.
Yeah, we can try another also. Yeah.
Yeah.
Yeah, for example, for just to comment more on this, after the first that is lower, the next epochs settle to a same timing. And for example, you can see here that it's 10 seconds per epoch. And the two GPUs you see not used as much as before. One GPU was being used at 80%, and we have two GPUs at about 60% each. Right, 60, 63, 64, around that. And then, yeah, it's 10 seconds, right?
Cool. So, yeah. So I will just like to comment about a bit about Nickel here. On NVIDIA's collective communications libraries, they use a variation of the all reduce mean operations. That's a kind of algorithm for the operations that reduce the target arrays for the processes for distributed computing. That's the figure that we looked up earlier. And I think so. Currently the the TF distributed mirror strategy use the NCCL all reduced class. That's by default. And yeah, we of course have the alternatives too. And that was given in reading a blog by NVIDIA, in which in Nickel 2.4 they implemented a double binary tree algorithm for the performance, and that scaled uh, uh, from the vanilla trees to approximately of course, on a particular data set that they used, it had approximately 180x improvement over when they were using it at scale with 24K GPUs. So that's the scale that they were working on. That's a totally particularly high performance computing environment. But yeah.
Yeah. I want just to show that using the 8 GPUs is going to how it is going to show, right? Just I want to show that, and he's saying that it should be the batch size should be a multiple of the number of workers. So let's put 80.
80, yeah.
And then run it, and we will see here that it starts to get slower, yeah, slower. And
the utilization will also...
Yeah, it goes lower on each. You have everyone busy, but only at about 20% or something like that. Yeah. Also, beside that, I was also looking at the CPU, and I was seeing that the CPU is more used. You have less idle time in the server. Like, for example, 16% idle, so it's more. The CPU is working more, right? But the GPUs are working less, something like that.
That's not fully saturated.
Yeah. The CPU doesn't get to 100%, right? But it's more busy. But the GPUs are less busy. Yeah, something like that. And
there was a recent
25 seconds.
Yeah, there was a couple of recent research that was done here with respect to the saturation of OpenGPT's the Microsoft strategy that they use in DeepSpeed versus the Google ones that they use. There are a couple of cool papers too.
Yeah. So my question is, how does do this guy like Google on those here, right? How do they get these improvements when these default libraries are not taking advantage of the 8 GPUs?
Yeah.
Yeah, I mean, I don't know if they do a different a model that doesn't get too much bandwidth saturation.
Yeah, go Reddit posts that are commented on with respect to the GPU saturation.
Yeah, or anyone know how to check the saturation on the GPUs, the bandwidth saturation?
That also depends upon the bandwidth separation, also depends upon the bottlenecks that you face. And for that, you will have to go through the, how do I say it, the data flow. And how do you try to prepare that? How do you calculate it? How do you try to
that would be a whole subject, right? Try to optimize
yeah.
the bandwidth and stuff like that.
Yeah, totally.
Okay.
That will be since some part of that flow, that data flow has a bottleneck on the all the layers. So there are a couple of good analytics and the data for measuring the data flow of a particular multi-graph. This is the links that I've shared. They are specifically with respect to the transformers and what they use from TensorFlow plus XLA, and they've compared the performance of TensorFlow plus XLA, then CUD, DNN, and the DSP. And then they have tried to summarize their optimization requirements on the performance improvements that they were able to achieve. Yeah, but there are a couple of frameworks that can measure the data flow across those layers. We can find the bottlenecks and we can try to optimize that and to come up with the saturation level.
Yeah, maybe that will be beyond the scope of or this or the book and or channel, right? Or this.
Yeah, this will completely then dive down to the optimization, the high performance computing, and that research.
Okay. Well, the training is done here. You can just predict on that model, and yeah, give us the results, right? The 7 here and the 2 here and the 1 here. And then after that, it comes the stuff about the multiple servers. And I don't know if we should do this on Sunday or because it's really late, right?
Yep, I think so. Was this might be the last chapter? Yeah.
Yeah, it is the last chapter.
Then we will What do you think, guys?
Let's see. So where are we? How far are we? How close are we to finishing? Or
we have to do the training on a model on a TensorFlow cluster.
Oh, okay, just finishing that. And that's basically the rest of the chapter, right?
Yeah, that's it. Yeah.
Okay, so shall we then just have another session on Sunday and finish up?
Yeah. What do you think?
Let's do it on Sunday.
That sounds fine.
Okay. Yeah. One little thing I have. I have to travel on Sunday, and I might come late. So, is there anyone that can start or?
I don't Nidin. Oh, he's not here. Well, we need somebody who's running the models like you are.
If we had access, we could start up with this too.
So have you run, Mayank, have you run the models on, have you been able to run the models on the notebook?
I have been only able to run it across my Ubuntu machine, but yeah, not in distributed environment. So that won't be much of a help here, but yeah, I can go through the text because into
sure.
this.
So yeah, so we can do that. And if you're late, Alvaro, that's okay.
Okay, thank you.
Yeah.
Yeah.
Well, thank you for taking us so far, and we're it's exciting. We're almost going to finish. I guess there's a few more lectures that people are going to give. Somebody's going to give a lecture on auto differentiation, a couple of I think one lecture on auto differentiation, and then someone's going to give summaries. I have to contact so the fellow who wants to give summaries of each chapter and see what his schedule is. Pardon?
Salim Chimlal?
Yes, exactly. Salim. Yeah. I have to contact him, see if he's still willing to do that.
Yep.
And he probably will be. So I think, yeah, we'll finish the whole thing very soon. And then we're starting the reinforcement learning class study group. And I forget what date we're going to do that. I think it's, I can't remember which date we had set as the kickoff.
I think so. It was the 4th was
the April 4th.
Yeah, was a holiday, so we thought of shifting it to 11th.
That's right. That's right. That's right.
And for the guys here who are joining from out, there's a time difference too. So
that's
from
right.
14th. Yeah.
That's
so
right.
this there will be a 1 hour earlier.
Yeah,
I think this Sunday, yeah, for Pacific time, this is a really nasty trick. Pacific time shifts for, and so everybody who's been keeping track of Pacific time and their local region, it all of a sudden shifts, and so you have to shift. The times are based on Pacific time. The meeting times are always based on Pacific time, so keep that in your calculations for the time. Yeah, we're gonna spring ahead. We're gonna be an hour later.
Yeah, that's a good point.
Because I remember one time this happened before, and so many people didn't come, and I wondered why, and it's because it's our fault. We switched times, and they didn't know. So,
No, but yeah. They would have joined in at the later time too, because we can try posting it in the chat too with respect to time.
Yes,
time difference.
That's a good idea. That's a good
yeah,
idea.
What if we put UTC time or something like that, additional to PT time?
Yeah, that's a good point.
All right, gentlemen, everybody stay safe.
see you guys on Sunday.
Yes, sir. Take care.
Okay,
Thank
take
you.
care, everybody.
Yeah,
Bye.
bye.